Good evening, everybody. Welcome to our first ever Zoom AP Calculus review session. Having a few technical issues here. I'm trying to play some music and it's not seeming to come through at the beginning, so I'm going to work on that a little bit. But I'd like to welcome students from both Avon High School and Lebanon High School. I know that this is our first session, so you might kind of wonder, hey, how's this going to work? What's the situation going to be? But hopefully you've all had a chance to look at the upcoming sessions, and I've got some slides here that I can cycle through to show you what's coming up. So let me run through that real quickly. Just run it through the PowerPoint here. So you got tomorrow night and Thursday night, we're going to have tables and Riemann sums. That's going to be presented by me. And then Mr. Passwater is going to take over on Thursday. And he's going to talk about particle motion. He does a great job with that. And then moving into next week, we've got 3 more sessions, Tuesday, Wednesday, Thursday, once again. Mr. Passwater is going to take the first 2, function analysis on Tuesday night, and then the ever popular rate in and rate out problems on Wednesday night. And then I'll come back and I will finish things up with just miscellaneous topics, some things that we didn't quite take care of. I have a few of these in mind already, but I am going to open this up for you guys to talk to either me at Avon or those of you from Lebanon. Let Mr. Passwater know about any miscellaneous things that you don't think that we quite covered, and I can make sure that I conclude that. So Thursday is going to be really tailor-made to you guys and what you want to see. All of these presentations are going to be recorded, and we will somehow get these out to you. They'll be probably housed on YouTube, and then you'll have a way that you can access. Likely you're going to do that through Canvas if you're at Lebanon, and you'll do it with Schoology if you're at Avon. And of course, you can see that you can get information about the meetings, the links, and the documents ahead of time. Some of you might have the document that we're using tonight. Don't worry if you don't. You can still follow along, and I think and pick up some things that certainly will work a little bit more effectively if you have the document. But no worries. I think there's something for everybody here, whether you're filling out the page or not. And with that, I think we are going to start. So I'm going to switch my view to my first slide here, which you might kind of wonder, hey, what's this all about? Hopefully it's now switched over. And I just want to talk a little bit about this whole idea of the free response question and where you would be when you begin the free response, because you've all taken mock exams. Believe it or not, there's some schools that haven't, and you guys certainly have a leg up on those particular schools. But both Mr. Passwater and I we hope that by the time you take your mock exam or your actual AP exam, in this case, the multiple choice would land you at the bare minimum, maybe at the bottom edge of the 2 range. Maybe some of you might be in the top end of the 1 range. That's okay, because it takes a lot of points to get to a 2. It takes 26 points for the sake of this particular scoring breakdown. These cut scores do vary from year to year. So it just sort of depends on, to some extent, the difficulty of the test, maybe. But by the time you get to a 2, things get easier for you. As you can see, it only takes about 17 points to get to the next band. If you find yourself at a 3, you can see it takes, well, I guess 15 points to get there. And maybe I should say it takes 18 points instead of 17 points to get to a 44. Now, I know that some of these might seem crazy, crazy big. It's like, oh gosh, 15 points, that's a lot of points. Well, it's actually not when you look at a free response question that you all know by now is worth 9 points. And you get 6 of these. So you get 6 opportunities to gain lots of points so you can start moving up this ladder. And the reason why I bring this to your attention is that the differential equation is sort of referred to as the treasure trove of points. At no other time on the AP Calc AB exam will you work a free response part of a question and receive more points than on a free response differential equation. And both Mr. Passwater and I agree that both his students and my students can all pick up lots of points there. We emphasize that in our course throughout the year. So that's going to be our hope, at least. If you have the document and you're following along, I wanted you to know that we are going to be looking at the 2016 problem first, which may or may not have made the Canvas upload. It's one that was added sort of towards the end. So if by some chance Lebanon students don't have this particular problem, and I'm going to fast forward to it right now, don't worry about it. Just sit back, watch this a little bit, kind of take in some of the detail, and then I'm going to follow this up with a problem that you likely will have in your document, which is the 2011, which is the landfill question. And then depending on what time is left, we might go to the potato problem. We'll see. Many of these problems, I know that both schools may have already seen way back in the past. But the thing about this now is that if you saw these like several months ago, you're going to have a different attitude about them now. You're a lot stronger students in calculus in general, and I think you're going to be able to latch on to these steps a lot quicker. So without further ado, we are going to start our 2016 AB4. So this is obviously a no calculator problem. Anything that runs questions 3 through 6 on the free response would be no calculator. It's very likely your differential equation question will not have a calculator. And 7 out of the last 8 exams have featured a differential equation. So it's very likely you're going to have a problem where you're going to solve a differential equation and find its particular solution. This particular problem starts off with this pretty tame differential equation, dy dx equaling y squared over x minus 1. And the first part is asking us to sketch the slope field on the axes provided. So what we're going to do here is just very systematically figure out where we're going to be drawing our little slope segment and what its particular slope would be. Now, you don't have to organize it exactly the way that I'm going to do, but I'm going to set up a T-chart, and I'm going to plug in some kind of an ordered pair, x comma y, and it's going to produce some kind of output, which would be the differential equation. And I'm just going to start in this upper left-hand corner, which is with the ordered pair 0, 2. So what would happen if I plug 0 in for x and 2 in for y? Well, we see that we would get 4 on top and -1 on bottom. Of course, that simplifies to -4. So we would somehow, some way, want to draw a line that goes through the point 0, 2 that would have a slope of -4. Well, that's not so easy to do because we don't have a lot of reference points around here. But here's the thing. A lot of people don't know about this. Mr. Passwater and I do, though. If you draw something that seems fairly negative, I don't know, maybe that is a slope of -4. Maybe it's not. Maybe I should make it a little steeper. Maybe it should look a little bit more like that. Well, I'm going to tell you, the readers for the AP exam, which both Mr. Passwater and I participate in, we're not going to get a protractor out and say, oh, that line's not steep enough. You know, we're going to dock students points for this. What we're going to do is we're going to look at that and say, this student drew a miniature tangent line that has a slope that's negative. Check, credit, they're going to be fine. So just make sure that you try to draw the right sign of the derivative, and you're going to be in pretty good shape. If we go to the point 0, 1, now this guy we can see is not going to be quite as steep. We're going to get 1 squared on top, and again that -1 on bottom. So I would say make this one not quite as steep, but certainly make it negative to ensure that you get the points. Okay. Now, when you get to the origin 0, 0, I think you're going to find a pretty easy result. You're going to get a y value of 0 and a -1 still in that denominator, and that's going to produce obviously 0. So you want to make sure you draw a horizontal line. All right, and that's what we're going to look for. We're going to look for a segment that is perfectly horizontal. All right, you're going to be drawing these freehand most likely, so just do your best. It's not a motor skill kind of issue, but you just want to try to make that horizontal line look like it's not got any positive or negative slope. All right, I think you guys pretty much get the drill. We're going to fly through these other 3 points. Typically, you won't do this with too many points because it will get very tedious. My thoughts is if a student can do this with 6 points, they can do it with 60 points. So if we use the point 2 comma 2, we're going to get 4 over positive 1, which is of course positive 4. So I'm going to try to draw a pretty steep positive slope through there. I think mission accomplished. And then we go to 2 comma 1. That's going to give us, see, 1 squared on top and 2 minus 1, which is 1 on bottom. So we're going to have a positive 1 slope. That's pretty easy to draw. We have a reference here at the point 1, 0. And then you probably can guess it at the ordered pair 2, 0. We're looking at another horizontal line, aren't we? A slope of 0 over positive 1. All right. I'll tell you what I'm going to do. We're going to break this down, and I'm going to show you the scoring rubric for each individual part. So we're going to move to that particular piece of the document, and we're going to see that the graph that they produce pretty much looks like ours. This thing would be worth 2 points back in 2016, and you notice that they just simply say, hey, if the student has the 2, 0 slopes, remember it only took 2 of those, we're awarding a point. So you didn't really break too much of a sweat to get that point, did you? And then if the other points have the right sort of complexion to their slope, you're going to receive the second point. All right, and most likely we'll look to see if these are positive or negative. But again, I emphasize, if you can really show a difference in their steepness, if it's pretty easy to do, make sure you do that. Because typically what will happen, the fewer number of points that you have in your differential equation plot, it's likely the more strict we might be as readers. All right, we're going to go ahead and move on to part B. Part B asks the students that if we let y equal f of x be a particular solution to the FRQ with the initial condition f of 2 equal 3, we want to write an equation of the line tangent to the graph y equal f of x at x equal 2, and then use this guy to approximate f of 2.1. This is probably the second most common type of question that's asked in a differential equation, behind, of course, solving the differential equation. So if you give me a second, I don't want to have to scroll back and forth, so I'm just going to rewrite that diffEQ really quickly. It was what, dy over dx equals y squared over x minus 1. Now, you want to be patient here. A lot of students are like, oh my gosh, I am so eager to solve this thing. I want to separate the variables and integrate both sides. That's not what the directions say to do. I got a feeling that's coming up, so you really want to read carefully what the directions call for. Otherwise, you're going to waste your time, and then you might have to draw arrows from one section to the other, which will read with you if you do a good job of that, but it's sort of a sign of weakness if you don't put the right work in the right space. And on the AP exam, you do have boxes very similar to what you're seeing in this document, but the boxes that you'll be using are probably going to be a little bigger. These are sort of condensed in order to save some real estate on my pages. Okay, so let's see, right equation of a tangent line. Is that something that we've ever done in class? You all better say yes. Whether you're from Lebanon or Avon, you better say yes, because we have done that hundreds of times probably. It's one of the most common questions that we ask. So the two ingredients to write the equation of a tangent line would be, of course, the slope and a point. So we need these two ideas. You don't have to organize your work the way that I'm showing, so don't worry about that. We'll look at the scoring rubric that'll kind of award the points for the minimum output. But for the slope here, it's very likely we're going to use the derivative. That's one of the main ideas of AP Calculus, that the derivative is the slope of the tangent line. So if we do that, when x is 2 and y is 3, we're going to get 3 squared, or 9, over 2 minus 1, which is a slope of 9. Now the point is pretty much staring at us in the face, right? This ordered pair 2 comma 3. So then all that we need to do is jump all over our point slope formula, which you learned from Algebra 1, to say y minus the y value of 3 equals 9, the slope, quantity x, minus the given x value of 2. Right? That'll serve as your tangent line equation, which you'll see here in just a moment. That will have earned your first point for this problem. And then the next point is you using the tangent line to approximate f of 2.1. So what you're probably going to want to do eventually is add this 3 over to the other side. So we'll get that done. I'm going to show you some fancy notation that I don't want you to worry about. But if we're finding f of 2.1, technically that would be approximately the same as the y function at 2.1. And in turn, that's equivalent to, well, if we add the 3 over and then finish up with adding the 9 quantity x minus 2, where the x is replaced with 2 minus 1, we've got really nice notation. But please understand, the stuff that I'm highlighting here in yellow does not have to be written on your paper in order to earn credit. Does it look good? We're not going to lie to you. It looks amazing. It's really strong work. It's telling me that you understand that this is indeed an approximation, and that by the time you get to the usage of the tangent line, using the equals is very appropriate. But if all you write is the 3 plus 9 quantity 2 minus 2.1 minus 2, or you compute that somehow, some way, you're going to earn that second point, right? We're going to try to model really good notation as we go through these sessions, just to kind of hold you guys to a higher level. Both of you, Leben and Avon, you come from very successful advanced placement calculus programs, so there's no reason why you couldn't do this. Now, if a student left it like 3 plus 9 quantity 2.1 minus 2, would the student get credit? And the answer is absolutely they would get credit. There's no reason why you have to simplify this, but if you wanted to, you'd have 3 plus 9 times 1/10, which is 3 plus 9/10, which basically becomes 3.9. But as long as you write something that is numerically equivalent to the final reduced result, you will get full credit. So the second point would be earned right there where I circled that expression in orange. Be careful if you want to continue to simplify things. You know, I don't want to necessarily talk you out of it, but just make sure that you don't make silly mistakes. You know, a lot of teachers will tell those students to not simplify anything, and that's quite fine. Want to look at the scoring rubric? This one's going to be very self-explanatory, I think. When we get down to part B, it is also worth 2 points. And you can see that the first point is given for the tangent line equation. This particular equation already had the 3 added over to the right side, but that is not necessary. Any equation with y and x would get the job done. That was equivalent to this equation. And then if you've got something that's numeric, whether it's what my hand is sort of underlining here, that would be perfectly acceptable, or of course the 3.9. All right. Let's move on to our part C for this question. This is where all the magic happens, guys. This is it right here. This is the only part left of the question, and if you do your math right, there's 5 points left. Remember, we talked about climbing that ladder. 5 points can make about 1/3 of the distance from one score to the next. And we're talking about you doing a problem that, you know, Mr. Passwater and I both think you're pretty good at. We just want to make sure that you get super confident. So the question says, consider that same differential equation. So great, I don't have to rewrite it. Find the particular solution to this differential equation using that same initial condition, f of 2 equal 3. So the very first thing that you learned when solving differential equations is that you need to separate the variables. So in this particular case, we've got this y squared up here in the numerator that we're going to divide over to the left side of the equation. So I would have 1 divided by y squared on the left side. And then I'm going to multiply the dx over to the right side. So I'm going to have this 1 over x minus 1 still hanging out on the right side, and a dx placed right after him. We cannot emphasize enough the importance of that step, because A, you're going to get a point for that. And you have to think about it. You haven't done any calculus. If you want to really think about what math class, which math class's skill, I should say, does this really go back to? And I think we'd all agree it's Algebra 1. you'll get a point for knowing how to separate these equations with Algebra 1. You would want to get the y's, in this case, on the left side, the x's on the right side. If by some chance something happens and you don't separate the variables correctly, a lot of things can go wrong and you can sacrifice a lot or possibly all of the points in the problem. We're not saying that to scare you. We have confidence in you that you can separate these. But what the advice that he and I would both like to give you is, don't just take an Algebra 1 step for granted. Really focus, concentrate. It's every bit as important as the calculus steps that you're going to do. All right, next step, you're going to integrate both sides. If you don't want to rewrite this thing to put integral symbols in front of both sides, my advice to you is don't. You can put the anti-differentiation symbols in front of both sides. We understand students do that. You will have already received the separation point, so you're good to go. So now we get to sort of practice our anti-differentiation techniques. So if we look at the left side, one of the most common mistakes with this problem, according to the chief reader notes, was that students saw the 1 over y squared, got real excited, and said, oh, this is the natural log of the absolute value of y squared, which is wrong, right? The integration of 1 over y may be the absolute natural log of absolute value of y, but not when we have a y squared there. So we want to make sure we don't abuse that logarithm rule. In fact, as I say to my students a lot, if 1 over y squared was having a dream, he would be called y to the negative 2. Because if he was called that, people would be able to take his derivative, and in this case, his antiderivative, a lot easier. So if we add 1 to the exponent and divide by that exponent, we have successfully taken that antiderivative, and as you might be able to imagine, you just earned your second point, and you probably haven't broken a sweat yet. Remember, what we're doing here is we're adding 1 to the exponent. Be careful, we're in negative number world, so when you do that, you get closer to 0. No need to put the plus c on the left side. We're going to worry about that on the right side. Now, on the left side, if you guys are really eager to use the logarithm rule, knock yourself out. This is going to be the natural log of the absolute value of x minus 1. Yes, you want to put absolute values, at least for the time being. That's important. This does not require a u substitution. You might think it's silly for me to write this, but I want to point this out. If you were to perform a u substitution, the derivative of that u in the bottom is going to be 1 anyway. Du over dx is 1, or du is equal to dx. So that just means you can freely substitute out this dx for du, and you just have a 1 over u form, which of course is natural log of absolute value of u. I just bypassed all of that because this had a pretty chill denominator. All right, now we're going to put the plus c on the right side. Always put your plus c with the side containing your letter x, or let's say if this was a real world modeling contextual problem, that letter will probably be a t for time. All right, you're 3 points deep into this, guys. All right, the next step, find c. And that's where this point f of 2 equal 3 comes from. Anything that I write in red is something that would not necessarily have to appear in your solution, all right? But I'm kind of using it to give myself a good blueprint. Anything that I write in blue probably should be in your solution. So I'm going to go ahead and plug 3 in for y. Now, as I do this, hopefully you're okay with me simplifying the y to the negative 1 by dropping him down to the denominator. I'll bring the negative out in front. So negative 1/3 would be equivalent to the natural log of, okay, what's 2 minus 1? Okay, last time I looked, that was 1. Positive 1 doesn't really need absolute values anymore, but you know what? It really doesn't matter because this is going to be a 0, right? One of those little things you want to remember. The natural log of 1 is 0. So you just found your c, and you also just found your 4th point. 4 points you've already earned for this problem. All right, so now let's see, I'm going to kind of move up here if I could, and I'm going to kind of take inventory of this equation. What do I have? So far I have negative 1 over y, if I sort of simplify the left side, equals the natural log back to the absolute value of x minus 1, and then my c is negative 1/3. Okay, now we said that we've earned 4 points already. There is going to be a 5th point for this problem, and that's basically to solve it for y. We want to get this y completely by itself. There's a lot of ways to do that. In this particular case, our best approach to this would be to probably maybe multiply through by the negative first, just to kind of get him out of the way. I don't mind if you lead off with a negative natural log, but I tell you what, since my 1/3 is going to be positive, I might choose to write it like this, but it really doesn't make much difference. And then at some point, we're going to come to the realization, oops, sorry guys, I didn't mean to confuse you. This is still 1/y. I haven't flipped anything yet. I just multiplied by a negative. And then at this point, we're going to have to flip both sides because we want y solved for. So, yep, you're allowed to do this. You can just take the reciprocal of the left side, take the reciprocal of the right side. Now, as I do that, watch what happens here. I'm going to get rid of those absolute values. All right, and I know that that can be a little confusing. And I don't want to make a big production of why they go away, but you can really attribute that to the fact that the x value that we were using for our initial condition was going to create a positive value within these parentheses anyway. So we don't really need to take the natural log of an absolute value that we know is already positive. Okay, it's very rare that the absolute values will ever stick around in your natural logarithm for a differential equation. In fact, it's happened one time in the past decade. And the reason is because we had an initial condition that had a negative y value, okay? I know that this y looks hideous. I know that it seems to violate a lot of rules of simplifying from maybe your algebra classes, but it's good. You know, you don't have to multiply the top through by a 3 and the bottom through by a 3. You could, but if you decide to do that, please be very careful. Right here, what you've got on paper, the stuff in blue will earn you 5 points. Let's check it out. Whoops, let's check it out here. So scroll down here, you can see the 5 points that you'd be awarded. Just going to double check. Okay, I feel good. That is the same answer. That would be pretty embarrassing if it wasn't. Pretty much the work that they have here sort of matches our work pretty nicely, doesn't it? You do not have to state the domain restriction. A lot of students see this on the scoring guidelines and think, no, I forgot that. You know, this is just one of those really cool mathematician things. They want to make sure that they put this here so that once a really hardcore high school teacher who's, you know, by the book says, well, we can't solve this, you know, unless X is between certain things. Well, we get that, but we're not going to make students do that on the AP exam. Here's your point for separating variables. You get 2 points for the antiderivatives. That's 1 on each side. Finding your C was worth the 4th point. And of course, getting Y by itself correctly would be your final point. This is the kiss of death, guys. This is the thing that we really want to make sure that you avoid. All right. We're confident that you're going to be able to do that. I know that my kids can avoid that. I've heard really great things about you guys at Lebanon, and I think you guys are going to kill that. All right. So we are going to go ahead and move to a second question that's a little bit more complicated. Again, some of you may have seen this. Students at Avon, you might really recognize the problem that we just did because I think it was on your Unit 10 exam. So that's kind of a blast from the past. Please keep in mind if any time that you have a question, I've got you guys all muted, but you're welcome to type a question in the chat. And I've got it sort of monitored and I can kind of address those questions if you have them. But you know, unless I see anything that you guys want to go back and revisit on this problem, let's go ahead and look at the 2011 question number 5, which is the landfill problem. Although this question seems to have a little age on it, it's what, 8 years old, so you know, you guys were like what, 3rd and 4th grade. It's still a very applicable question. It's a great model of what you could likely see on the AP exam. The difference between this question and the one that we just did is that this one has a little connection to the real world. See my little picture? See all this garbage up here? Yeah, gross, right? So it's kind of giving us a little bit of flavor of what the problem's going to address. So this was an AB/BC question. So sometimes the BC exam, which I know that some of you that were watching this video might be BC students. I know that my students at Avon that are BC students are going to watch these tape delayed to get their review in. But this is certainly fair game on your exam as well. So problem 5 from 2011 says, at the beginning of 2010, a landfill contained 1,400 tons of some solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy this differential equation, dW dt equal 1/25th quantity W minus 300 for the next 20 years. W is measured in tons, and T is measured in years from the start of 2010. First question. Use the line tangent to the graph of W at t equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010. Now, the first 3 months could be bothersome. It's like, what do I use for that? They did help you out. They said on the exam that year that that would mean the time is 1/4. 3 months is 1/4 of a year. So I hope that you see a connection. This problem looks very similar to part B of the problem that we just did. You're going to use a tangent lines equation to approximate. So let's do that. So we need slope, right? And we need a point. So what I'm going to do for the slope is I'm going to use the derivative, the differential equation. And notice in this differential equation, I only see the letter W. That's not a bad thing. It's actually an easier thing because you only have one thing to plug in for. And we have to think wisely. What is W, let's say, at the very beginning when time is 0? Because that's when we want to write the tangent line. Now, does that mean that we plug 0 in for W? All right, you don't have to say no in the chat, but you're welcome to if you want to. But no, we don't want to put 0 in for W. We have to think about what is the amount of waste W at that moment. And if we read in the problem a little bit, it says that that W is 1,400 at the beginning. So I know that that's a little tricky. It's sort of a disguised value that you have to plug in for there, but that's going to help you tremendously. So you've got 1/25th times the quantity 1,400 minus 300, and wow, that's complicated. That's tricky, isn't it? That's like terrible. What is that? That's 1,100 over 25. See, here's the thing. This is not a calculator permissible question, but 1,100 divided by 25 actually is a very nice number. If you actually wanted to divide 25 into this, you get 44. Now, fear not. If you used 1,100 over 25 throughout the entire part of the problem, you would be okay. You would get full credit. All right, we also need a point. Well, I think we've pretty much established that the ordered pair is 0, 1,400. All right, remember, we're trying to find the tangent line at that particular moment. Okay, now I know I wrote this in red, which might be a little deceiving. So I kind of want to show you in blue, what is it that we really want from this problem? Well, we want the student to make sure they establish the fact that dW dt, at time equals 0. Now, you don't have to show that notation, so don't worry about that. But we want somehow some indication that that's the 1/25th times 1,400 minus 300, or equivalent eventually to 44. So I really strongly encourage you to use good notation. Try to establish the fact that the dW dt is this 44 number. We kind of look the other way. I mean, if a student were to do this, dW dt equals 44, that's not awesome because it kind of implies that the dW dt is always a constant. I've seen some detailed scoring reports, table notes from differential equations where we do allow for that. This is awesome, though. This is really good technical notation. All right, and there's lots of other notations that you could use for that instead. Okay. So you got your 44, you got your point. I think we're ready to write an equation. What do you think? So what variables do you all like to use for your equations, for lines? I'm going to go out on a limb and I'm going to say X and Y. Is that what you all like? Because if you like X and Y, that means that you are normal. That's what most people like. So you just simply dig in and say, okay, Y minus the 1400 equals the slope 44. And okay, let's use X. Now, the independent variable in this problem really isn't X, though, is it? If you think about if there were a graph that depicts all of this action, the horizontal axis isn't X, it's T, isn't it? And the y-axis is really a W whenever you have this curve, you know, whatever this curve will look like. I doubt it looks like that, but for example, we might say that. And then the tangent line, you know, right here would not necessarily be a function y, or W, sorry. We might call it y, but it should be in terms of t. But we're not going to have you guys worry about that, because the funny thing about the AP exam, as readers are concerned, an X that a student writes, if one looks at it a little differently, looks like a T, right? So you can sort of interchange X's and T's in a lot of situations on the exam. If you feel very confident that T is the variable that's going on, I would just go ahead and stick with that. You know, and I'll be honest, I like T better. It's stronger. It shows that the student has a little bit better command of what's happening, but please understand, X would work. All right, now at this point, we want to figure out what is happening at time 1/4, because, oh, now that makes perfect sense. Plugging in 1/4 for T does kind of seem logical, right? So Y of 1/4 would be, I'm going to add the 1400 over if that's okay. And I have 44 times 1/4. And I'd end up with 1400 plus, what is that, 11? And I think that's 1411. 1411. Now, fear not, if you used this for your slope and not the 44, you might have some hideous numeric value here that you care not to simplify. As long as it's equivalent to 1411, you would earn the points. Now, I want you to listen to this advice really carefully. Sometimes units are very important to your answer. On the AP exam, it's typically the case that 50% of the time we might not award points for an answer if it doesn't have limit or a unit, and 50% of the time we look the other way. I don't want you students, whether you're Lebanon or whether you're Tigers or Orioles, I don't want you guys taking any chances. Let's put units for every single contextual answer that you come across to play it safe. And what we're looking for here is, you know, use the value here to approximate the amount of solid waste, and the amount of solid waste, of course, is measured in tons. Okay, now if we look at the scoring rubric for this, first thing I want you to look at is this really lovely global mean. Check that out. Students across the nation on average scored 1.6 out of 9 points on this problem. And BC students scored a 3.5, which is still not the greatest, especially for BC students. You know, I'm sure Avon, Lebanon probably were a little bit above the averages on those cases, but there are a lot of schools that are even below, because this is a mean. So if we look at choice A, or part A at least, we can see that 1 point would be awarded for the DWDT. All right, so that's basically finding that 44 or whatever is equivalent to it. And then you'd get a point for this answer of 1411, or some expression that's equivalent. All of this stuff that's really doctored up over here may not be very necessary. So don't worry, don't panic about having this wonderful notation. Wonderful notation really is developed over time. It's something that if you have been really bad at from August to May 1st, tomorrow, it's really hard to get good at that in 2 weeks, but it's not a lost cause. And we would encourage you to try to identify things that you're finding. If any of you are talking about majoring in a STEM field and you study more advanced math and science, you're certainly going to want to use good notation, because you're going to be writing reports and producing things that are going to be read by other people, professors, fellow peers in your class, and you want them to be able to follow what your mathematics work is saying. All right, let's move on to part B of this particular landfill question. And in it, we are asked to find the second derivative, d2w dt2, which is just notation for the second derivative of w with respect to t in terms of w. So we want to use that to determine whether your answer in part A is either an underestimate or an overestimate of the amount of solid waste at the time t equal 1/4. Now, the key here, finding the second derivative is just the derivative of the first derivative. So if you don't mind, again, so I don't have to scroll back and forth, I'm going to recreate that first derivative. I know it's already on your page, so you're fine. So it was 1/25 w minus 300, I think. So we have to take this derivative. We're going to do so with respect to t. The left side is just fancy schmancy notation. And the right side's where all the action is happening. So the 1/25 drops straight down as a constant will. And now if we take the derivative of w, well, normally that's like a constant, or I'm sorry, a variable with a coefficient of 1. So you would get 1, and that's true. But since we're differentiating with respect to t, we have to tack on that dw over dt in this particular case. That's something that we call implicit differentiation. You're really using the chain rule. Anytime that your variable differs from your independent variable down here in the bottom, you always tack on that extra little piece. A lot of you might remember using that in implicit differentiation. And I think, Lemon, you're going to be talking about related rates here very soon, kind of recapping that idea. That's a very prominent feature of that particular topic as well. Now, when you get to the derivative of 300, you're going to have 0. So we are good, guys. This is it. Sort of. What do I mean, sort of? Well, this dw dt is not very in terms of w-ish, would you say? We want to get this dw dt out and have something in its place that only has w in it. We don't have to look very far to find that. So we're going to basically replace the dw dt with the original expression, 1/25 quantity w minus 300. That's going to earn your first point right there. Now, we're asked to determine whether or not the answer in part A is an underestimate and overestimate. And what I want to do is kind of recap the whole idea about these estimations with these curves. The only way that you can get an overestimate is if you have a solution curve, let's say, that looks like this. And the tangent line can be drawn to any point. Take your pick, guys. We can put it anywhere we want. If that tangent line is affixed to that, you see that all of the y values on that tangent line, wherever you may be, are going to be above the curve. The only exception is at the point of tangency. Now, what feature does this curve have that makes that true? It's concavity. Now, some students might say, no, it's whether or not it's increasing. Well, no, I can prove that. I can draw a concave down curve that would be, let's say, decreasing. What's concave down decreasing? Does that get the job done, you guys? So if I look at a tangent line anywhere there, isn't it still an overestimate? And then the magic of my little software here, maybe this will work. This might be a disaster, guys. Well, sort of a disaster. If I draw my curve, whoa, it's going crazy. If I draw the curve where it's now concave up, and if I affix a tangent line, and if it cooperates, this would be awesome. If I affix a tangent line somewhere, then obviously we can see that we have an underestimate. Concave up, underestimate. Hey, that's a nice mnemonic, isn't it? Up, under. We'll begin with you. Use that. Down, over. Okay, not so good of a mnemonic there, D and O, but the concave up and underestimate will work nicely. Now, that's where you're at. You want to determine, is this graph concave up or down? connect concavity with the idea of the second derivative. So we want to figure out, is this particular expression positive or negative? That's a good question. I don't know. Depends on what W is, right? I need to figure this out. Well, they're asking us to do this specifically at time 1/4. When do we remember that value t equal 1/4? Did that come into play somewhere? Oh, that came into play like way over here, didn't it? And that's a pretty large W in that case. There's no way that this thing here is going to be a negative number. So we are very certain that our second derivative is going to be positive. Now, I don't like saying that necessarily because I don't know how much truth there is to that, because there could be a moment maybe when the trash is less than 300 and then I've just told a lie here. So, maybe I could follow that up and be a little bit more precise by saying on the interval, since we started this experiment when there was 1,400 tons of garbage, up to the time when there is now 1/4, which is sort of when time stops for us in this problem. We don't really care what happens after 1/4. That might be a little safer. All right, now fear not. It's very likely that you do not need this inequality. Now I say very likely. The exam sort of changes a little bit from one year to the next. That there are question leaders that have different standards for what students write. I will probably tell you that if this was required on a certain problem, there'd be a ton of students that would not get the point for this. So you may be fine just to say that the second derivative is greater than 0 because you're kind of talking about locally in this particular region, but this is a lot more powerful. And if you can kind of add that, that would be awesome. The only thing is we haven't officially answered the question. So we could say, therefore you don't have to use that symbol if you want, but you could say the answer in part A is, what is this again? See, since we're concave up, that'd be an underestimate, wouldn't it? Underestimate. And hopefully that makes sense. You guys are awfully quiet in the chat, but I take that is a good thing. I think part of the reason why you're quiet is that anytime that we do sessions with students from different schools, I know it's kind of tough to be that first one to bring out in chat. But again, if you have a question, please feel free. You can access the chat by basically going up into your little ribbon for your Zoom. There's a button called More, I believe, and then you can access chat there. All right, we have one final part of this question, part C. I've just rewritten the stem here, so we've already kind of gone through that. And it asks now to find the particular solution to this differential equation with the initial condition. So this reads very similar to the question that we just did from 2011. It's just in context now. So instead of y's and x's, you have w's and, well, I guess t's, right? So the w is the dependent variable. He wants to stay on the left side. So this w minus 300 has to move over. Since he's being multiplied by the 1/25th, we are going to divide it over. And lo and behold, we would have 1 over w minus 300. And then I'll keep the dw right there. I could put the dw up here. It would be fine. And then on the right side, I have a 1 over 25. It's going to sit still there. And then the dt is going to multiply over. Would you all agree that you have w's on the left and t's on the right? Strong. So we're just looking at earning 1 point here. We've got our foot through the door. Integrate both sides. Now that's not worth a point yet. You got to actually do something. So if we look at this, hopefully we see that this is another natural log of absolute value of w minus 300. Right? It's not all the time that you get a natural log for differential equation problems. I would say it happens fairly commonly. On the right side, the integration antiderivative of 1/25 is 1 over 25t. plus your constant of integration. This is a problem where you would have only earned 1 point for having integrated both sides. The reason is the right side is pretty puny and easy to do. Now you're going to use the initial condition. That condition is the ordered pair 0, 1400. So we will plug that in, and that would give us the natural log of 1400 minus 300 is 1100. And that would be equivalent to 0 plus c. So the c is the natural log of 1100. Now I want to say something right here just to make sure that everyone are on the same page. There are two different camps in solving differential equations. And I always teach it to my students that I would rather them solve for c first before getting the w by itself. I know a lot of teachers that tell their students, in this case, solve for the w first and then get the c. And some of these teachers have absolutely phenomenal AP scores. So I'm not going to be in any position to tell them that they're doing it wrong. It's just a different philosophy. I think it's a much easier thing to do to manipulate something after the C has become a number. All right, so if this varies from some technique that you've seen, even I have some students in my class that maybe watched a video somewhere, Khan Academy, and W was maybe solved for in these types of problems, and they were doing a good job of it, and I didn't change the habit. Right? But you're going to find that I typically like to find the C. All right. So we are now going to tell you what, I'm going to jump up here so I got some more space. I'm going to kind of take inventory. Where am I? I've got this natural log of W minus 300, equals 1/25 t. And I've got my wonderful but yet ugly looking C, natural log of 1,100. All right, our next job is to get W by itself. Right, we got to solve for this thing. Now this is going to be a little bit more challenging than getting the Y by itself in the previous problem. We have a very special magic trick. That magic trick is called the idea of exponentiating. If you have a natural log that you want to get rid of, in fact, two of them, we are going to have you take E as the base of both sides. I'm going to wrap all this stuff up in parentheses to make sure I know it's all the exponent. Okay? Now, note, that's not called raising both sides to the E power. Right? It took me a long time, but I looked through several books, and they actually call it exponentiate both sides with base E. Cool thing about this, E to an ln power, as long as there's nothing in front of the natural log, will sort of, I don't like to use the word cancel, but that's sort of what happens. And we would end up with the W minus 300. I'm going to keep that in absolute values just for the time being, but that's going to change here in a little bit. Over on the right side, we have a very cool property. It's a property from algebra that says that if you have E to the sum of two different pieces of an exponent, that can be written as a product of two different bases of E. Now, if that's a little bothersome to you, if you think about this in reverse, whenever you multiply two like bases, haven't you always added the exponents together and then wrote the base once? It's the same idea. It's the same rule. It's just that you're going backwards with it. You're not used to that. You don't go backwards with that rule very often. In fact, you probably do it more in calculus. You ever did it, say, in Algebra 2 or pre-calculus. The cool thing about this is that this E to the ln sort of eliminates each other, and then you just have this 1,100 on the right side, I'm sorry, as the coefficient, and then I could put the t over 25 if I want. And then look what happens. Magically, absolute values disappear. Say, what? How's that going to happen? Well, again, your W value in and around this scenario was 1,400. And that means that this is always going to be positive. In fact, we're never going to really get to a situation where we have probably less than 300 tons of landfill. Think about it, guys. What happens in a landfill? Is trash brought in or taken out? Well, it's brought in. It's only going to get bigger and bigger and bigger. All right, last step, add 300 over. And you're looking at this guy right here. No need to, but if you wanted to, you could let W put on his Sunday best close. Yep, variables have Sunday close. That would be W of T. This makes him look a little bit more official, but no, it is not a requirement. And that would be a very, very awesome fifth point. Let's take a look at the scoring rubric. You know what? Did I forget to take a look at the scoring rubric for B? It looks like I did. Well, we can look at that one real quickly. It was worth 2 points. You remember all the way back to that question, taking the second derivative and getting an expression that's somewhat equivalent to this in terms of W, be worth the first point. Did I put 1 over 625? I don't remember. What did I do? I don't remember. Well, I didn't. I wrote 1/25 times 1/25, but isn't that the same as 1 over 625? So I would get credit for that. Don't have to simplify. And then, of course, stating that the second derivative was positive, and then thus the underestimate would be your reason point. Going to the differential equation, this is not going to surprise you because there's 5 points left in the problem. Once again, it looks like the work that I showed seems to model the standard here. I mean, almost step by step by step. They threw in this little idea about the time has to be between 0 and 20. If you kind of read lines in the text of the problem, it states that sort of indirectly. Don't worry about it. This is not required for credit. Point distribution is a little different where you only get 1 point for both antiderivatives, like I said before, but there is a separate little point by remembering that there's a plus C in the problem. Kind of nice. I will say that this doesn't seem to be as common anymore. They tend to kind of consolidate these 2 points in the last few exams. And unfortunately, you guys, I hate to break the news, but it's more likely that you have a 4-point differential equation problem nowadays than a 5. But sometimes you might have a second piece to this or another piece that might say, you know, approximate W of sometime 7, and then that could be another point perhaps. Okay, but hey, don't worry about it. If it's worth 4 points, 5 points, remember that's still a pretty nice jump in that scoring slide, that bandwidth scoring slide that I showed you at the beginning of the broadcast. All right? All right. Taylor, thanks. That was helpful about probably solving for the C first, because I was kind of worried about that, because I didn't really talk to him about how he had you guys solve your differential equations. He and I do some things very differently, but I think we're both very effective. He's obviously a fabulous, fabulous teacher. You guys at Lebanon are very lucky to have him, and I can't wait for my students to be able to see some of his sessions later in the week. So, guys, it's 9. I told you it's an hour, so I think that's pretty much where we're going to stop. So I'm sorry I didn't get to do the potato problem, but you have it. I know the students from Lebanon, you guys have worked this before, but it's been a while. The potato problem is very popular in that it was the most memed question in the history of the advanced placement test. In other words, when the students finished the exam in 2017, they remembered this problem so much that they started kind of Instagramming and tweeting funny pictures of potatoes because they were so frustrated with the question. I don't think it was so bad. I think both of our schools did a pretty good job with it, but the rest of the country didn't seem to like it. We can make a solution key available for this problem if you guys want to kind of play around with it on your own. Obviously, there's 2 more questions that are in the packet, the potato problem and the landfill. My students, we're going to see these 2 problems, either some of them Monday or Friday of this week and Monday of next week, but they're always going to be in the packet for you guys to practice. And so if there's no other questions in the chat, I'm going to hang around for just a few minutes. I'm going to go ahead and stop the recording so I can start processing this, but we are pretty much done, and I hope that this was worth your while. And I'd like you to tune in tomorrow when we talk about tables and Riemann sums. So I really appreciate you guys hanging around. And let me know if you have any questions. I'll stick around. Otherwise, have a great evening, you guys.